Hello students, welcome back to next session in this unit number 4, where we are going to discuss about Gibbs Dalton's law. So the topics which are there in this unit are properties of moisture. This is what we discussed in earlier session, and now we are going to discuss Gibbs Dalton's law, and these are the topics which are remaining in this unit, and we will be discussing now Gibbs Dalton law. So it is a very simple topic. We will see in 25 minutes time. So Gibbs Dalton law and ideal gas behavior. So here both dry air and water vapor can be considered as perfect gases. So this is what we have seen in earlier session, and both are considered as perfect gases since both exist in the atmosphere at low pressures. Hence, perfect gas laws can be applied to them individually. So perfect gas laws, perfect gas laws we can apply here for these both dry and water vapor for both gases. In addition, Gibbs-Dalton laws for non-reactive mixtures of gases can be applied to the dry air not only to obtain its properties as single pure substance before establishing the properties of moist air. So here Gibbs-Dalton's law is applied for non-reactive mixtures of gases can be applied to the dry air not only to obtain its properties as a single pure substance before establishing the properties of moist air, and these properties we have discussed in our last session. So all those can be established here. So Dalton's law of partial pressures, this is already we discussed in earlier session, but we will elaborate this, we will discuss more about it. Consider a homogeneous mixture of non-reacting ideal gases 1, 2, so gas 1 and gas 2, etc. at a temperature T, pressure and occupying volume as shown in figure A. So this is the figure A. So gases are there, homogeneous gas mixture, and gases 1 and 2 and volume and its volume. So here we have a thermometer and we have a pressure gauge. Let the number of moles of individual gases are N1, N2, etc. And then respective masses will be M1, M2, etc. The total mass M and the total number of moles N are M equal to M1 plus M2 up to the summation of Mi. So all the gases, so for each individual gas are summed here to obtain the total mass. So it is the total mass is summation of all the masses, and each mass is relevant to each gas, type of gas, and N is equal to N1 plus N2 plus, so that is the number of moles. So number of moles are summation of all the gases, that is moles, number of moles of each gas are summed here to get the total number of moles. So where I is the number of each gas. So how many number of gases are there in the mixer, and those many number of moles are we have those many number of n's here. So in the Dalton's model, each gas is conceived of existing separately at temperature T, and the total volume V of mixer is shown in figure B. So that is in next diagram. So this is the Dalton's model, and here this is the gas 1 and gas 2, and which are separately treated here in Dalton's model, and after measuring the temperature, volume and pressure, we can sum them to get the total mass, total mole number or mass. So Dalton's law of partial pressures here If one if one were to measure the pressures exerted by individual gases, they would be found to be P1, P2, P3, etc., etc., and less than the total pressure of the mixer. So total pressure, when we see the P1, P2, definitely each one will be lesser than the total pressure in that mixer. So these are referred to as partial pressures. So this P1 and P2, these are all referred as partial pressures since they are lesser than the total pressure. Considering mixer and a component gas existing separately at a T and V, we have the binary gas mixer. So that is PV equal to nRT. So this is the perfect gas law equation. And P1V equal to N1 RT. So that is equal to N1. So N1 can be found out, the mole number can be found out, P1V by RT. So similarly for P2V equal to N2 RT. So where N2 can be found out using P2V by RT. So substituting N1 plus N2 equal to N, so that gives the P equal to P1 plus P2, or P total pressure is equal to summation of all the pressures. So thus for a mixture of ideal gas, the total pressure P is equal to the sum of the partial pressures. So this is known as Dalton's law of partial pressures. So this is the Dalton's law of partial pressures. So please remember that. So the pressure, the total pressure is equal to summation of all partial pressures. Obviously, each partial pressure is lesser than the total pressure. So that is the Dalton's law of partial pressures. Next, we have Amagat law of partial volumes. So now Dalton's law is described with respect to pressure, whereas Amagat law is with respect to volume. So it is Amagat's law of partial volumes. So in the Amagat model, each component gas is considered as existing separately at the total pressure P and the temperature T of the mixer is shown in figure. So I will show you this figure. So this is Amagat's law. So here the total volume is equal to V1 plus V2. So that is the gas 1 plus gas 2, and at the pressure and temperature, measured temperature. So once you measure separately for each gas, so that will be equal to total volume only. So this V1, if you measure separately, if you have separately, and if you have volume 2 separately, if you mix up both, so that gives you total volume. So here also the partial volumes existing. So let the volumes of individual gases under these conditions be V1, V2, etc. These are referred to as partial volumes. So now as we see in partial pressures, here also partial volumes existing. Again, applying the ideal gas equation of state 2 mixer and components we have. So PV equal to nRT, so that is the mixer. So N can be calculated PV by RT. So PV1 equal to N1 RT. So N1 can be calculated using PV1 by RT. So from this equation. So similarly for PV2 equal to N2 RT, and N2 can be calculated, or N2 can be found out from PV2 by RT. So substitution in N1 plus N2 equal to N. So that gives V equal to V1 plus V2, or V equal to summation of all partial volumes. So V1, V2, V3, all these volumes are called as partial volumes. Thus, we see that the total volume is equal to the sum of partial volumes. This is known as Amagat's law of partial volumes. So the ratios V1 by V, V2 by V, etc. are referred to as volume fractions. So volume fractions are nothing but the volume of first partial volume divided by total volume. So that is the V1. So that V1 by V, and that is referred as partial volume. So partial volume percentage we can calculate. Next, we have mole fractions of component gases. Mole fractions, in first session we have seen moles also for component gases. So it is seen from above section that, so Pi by P equal to Vi by V, so that is equal to Yi. So Yi, so where the ratio of partial pressures to volume pressure and volume fraction are equal to the mole fraction. So Yi is known as mole fraction of that gas. It also shows the both Dalton's law and Amagat law are equivalent. So from here we can say, or we can conclude that Dalton's law and Amagat's law are equivalent. Since M equal to M1 plus M2 and M equal to Mn, and M1 equal to M1N1, M2 equal to M2N2, and then we have Mn equal to M1N1 plus M2 and N2. So here this is the equation, and we have M total mass is equal to Y1 M1, that is the fraction, and Y2 M2 are M equal to sigma Yi Mi. So summation of Yi and Mi, where M represents the molecular mass of the mixer. Note that N1 equal to M1 by M1 and N2 equal to small m2 by m2, and etc. Similarly, for the mixer, N equal to small m by m, capital M. So this is the mole and the molecular mass of the mixer. So that can be calculated. Capital M can be calculated using this relation, M equal to sigma I, Yi and Mi. Next, we have Gibbs theorem. We have seen delta law, Dalton law. We have seen Amagat's law and Gibbs law, and then Gibbs theorem we are going to see now. And Gibbs theorem, it further indicates that the internal energy of a mixer is equal to the sum of internal energies of individual components. So it states actually that the energy of mixer is equal to the sum of internal energies. So that is with respect to enthalpy and of individual components taken each at the temperature and volume of the mixer. Thus, we have the internal energy of the mixer, and that gives as mu equal to m1 u1 plus m2 u2, and this is known as Gibbs theorem. And it can also be shown that the enthalpy and specific heat of the mixer can similarly be written as. So here this is in terms of the enthalpy and specific heat, mh equal to m1h1 plus m2h2, and mc equal to m1c1 plus m2c2. So composition of dry part in atmospheric air. So I'm going to show you one a table like we did in earlier session. This table summarizes the key properties of primary constituents of dry air, showing their molecular mass part by volume and part by mass. So same similar table I wanted to revisit here, and the same table we have already discussed. Just we will see by component wise. N2 nitrogen, it is 28.02 part by volume. So this is part by volume, it is 0.7803, and part by mass it is 0.7547, and oxygen in terms of molecular mass it is 32, and by part by volume it is 0.2099, and part by mass it is 0.2319, and argon AR, that is 39.91 molecular mass, and 0.0094 by part by volume, and part by mass it is 0.0129. CO2 carbon dioxide 44 and part by volume it is 0.003, and part by mass it is 0005, and hydrogen it is 2.02, and part by volume it is 0.0001, and part by mass it is 0. And this table summarizes the key properties of the primary constituents of dry air, showing their molecular mass, part by volume, and part by mass. So in earlier session we have seen a very similar table for these components only, and these values are essential for calculating the average molecular mass of dry air. So dry air average molecular mass can be calculated using this table, and the gas constant of dry air and mass are mole fractions of gas mixture analysis, and application in Dalton's law, Avogadro's law, and Gibbs theorem. So in all these three theorems are all these calculations. So that is partial pressure, and in Avogadro's law partial volume, and Gibbs theorem. Everywhere we can apply this molecular mass. So molecular masses and gas constants for dry air and water vapor. So I will give you this. Please remember these values. If it is not given in the problem statement, you can assume, and you can use make use of these values directly in the problems in the exam. From the respective mole fractions and the molecular masses of component gases, the molecular mass of dry air part may be computed. So for this purpose, it may be observed from the equation that part by volume represent the mole fraction. So there is a equation, and this is the equation. Thus, using the values for mole fractions from table, we have MA equal to sigma yi into capital MI, and by using all the values, those are given in the earlier table. So here all we are adding, and we are getting this 28.966. So that is the MA value, so mole fraction value, where subscript A denotes dry air. So knowing that the values of universal gas constant, so universal gas constant is 8.3143. So please remember this value. You are going to apply this everywhere in most of the problems. While solving the problems, this value is very handy. You have to remember this. It is 8.3143 kilojoules per kg mole Kelvin. The gas constant for the two parts of moist air are as follows. So that is for dry air, it is MA equal to 28.966. So RA can be computed 8.3143. So that is the universal gas constant divided by MA. So that is equal to 0.2871 kilojoules per kg Kelvin. So this is the RA value. So for water vapor, so for vapor, that is the wet air, so MV equal to 18.016. So that is equal to RV. RV can be gas constant can be calculated 8.3143 divided by 18.016, that is equal to 0.461 kilojoules per kg Kelvin. So this can be computed, and you have to remember only this value, where subscript V refers to water vapor. So we will see one example to solve this problem. It will be more clear, and you can easily remember the values also. 1 cubic meter of H2 at 1 bar and 25 degrees Celsius is mixed with 1 cubic meter of N2 at 1 bar and 25 degrees Celsius. For the mixer at the same conditions, find the mole fractions of components, partial pressures of components, mass fractions of components, and molecular weight of the mixer, gas constant of the mixer, volume of the mixer. So these components all we have to find. So very simple problem. We can apply those equations already we have discussed, and we can easily solve this problem. So first one is molecular weights. So M1 equal to MH2, so that is equal to 4.003, and M2 equal to MN2, that is equal to 28.02. And with that, gas constants R1 and R2 can be calculated, and that is 8.3143. This is universal gas constant divided by M1, and we are getting 2.077 kg per kilojoules per kg Kelvin. And similarly, R2 equal to universal gas constant divided by M2, that is equal to 0.2967 kilojoules per kg Kelvin. And the masses we can calculate. M1 can be, M1 is equal to P1 V1 divided by R1 T1. So R1 we know, and we know P1 and V1, and T1 is also known, and it is 293 298. So we are getting M1 equal to 0.1616 kg. Similarly, M2 can be calculated using P2 V2 by R2 T2. So 1 into 10 to the power of 5 into 1 divided by 0.2967. So 0.2967 R2, and into 10 to the power of 3 into 298 equal to 1.131 kg. So that is M2. So total mass is equal to M1 plus M2. It is 1.2926 kg. So total mass is 1.2926 kg. So number of moles, N1 equal to M1 by M1, small m1 by capital M1. So that is 0.0404. N2 equal to M2 small m2 by capital M2, 1.131 divided by 28.02. So that is equal to 0.0403. And total mole number, so number of moles, total number of moles equal to N1 plus N2 is equal to 0.0404 plus 0.0403. It is 0.0807. Mole fractions, so we know N1 and N. So N1 by N Y1 mole fraction Y1 equal to 0.0404 divided by 0.0807. It is 0.5. And Y2 equal to N1 N2 divided by N. It is also very much 0.5 only. So partial pressures P1 equal to Y1 into P. So that is 0.5 into 1, 0.5 bar. P2 is also 0.5 bar. Mass fractions M1 divided by total mass. So 0.1616 divided by 1.2926. It is 0.125. M2 by M2 by M1 M is equal to 1.131 divided by 1.2926. It is 0.875. So molecular weight of mixer, it is equal to capital M equal to Y1 M1 plus Y2 M2 equal to 16.01. So gas constant of mixer R equal to R bar divided by M. It is 8.3143, that is universal gas constant, divided by 16.01, that is equal to 0.5193 kilojoules per kg Kelvin. And volume of mixers V equal to mRT by P, and that is equal to 2 meter cube. So 2 meter cube. And also from equation V equal to V1 plus V2, so total volume can be find out here. It is 2 meter cube. So that is about the problem. And the, the, to refer this problem and content of this session, You can refer CP Aurora book, Refrigeration and Air Conditioning by CP Arora, and you can refer Rajput and also Kurmi. That also gives you few numerical problems, and you can rely on these books. So there ends this topic. Second topic, Gibbs Dalton's law. So in next session, we will see the next topic from Unit 4, and we will be meeting again in the next session, students. These are the books. We stop here. Thank you, students. We will meet again in next session.